Hi, yeah, so I'm Alex. I'm with the AWS Center for Quantum Computing, and this is about quantum machine learning. I just wanted to start with sort of a disclaimer, which is that quantum machine learning is a really large and eclectic field and involving a lot of topics and people from a lot of different places. And so I think one's perspective on it is really shaped by at what angle one comes at that from. So for me, I come originally from physics and to some extent theoretical computer science. My, I guess, working expertise is in quantum algorithms. So, I would really not at all call myself an expert in normal machine learning, but here I am talking about quantum machine learning. So I think you guys should definitely understand my opinions and this talk in the context of me thinking about quantum machine learning as another avenue to apply quantum algorithms to. And then I should also say that at the quantum algorithms team in the AWS Center for Quantum Computing, and by extension me, we're kind of more interested in thinking about far-term algorithms that can be run on fault-tolerant quantum computing. And so this, to some extent, shapes how I think about quantum machine learning as well. But many people approach this from a more near-term perspective. Okay, so maybe some goals for the talk. Hopefully I can communicate why we might hope that quantum computing could be good at machine learning in the first place. I guess also what are the technical challenges to actually making that happen. Hopefully inspiring some ideas on how applied math might help. And what is an outlook for quantum machine learning that can maybe be compared against some of the other application areas that are going to be talked about later today. So this is just a very basic kind of flowchart of what a machine learning situation might look like in general, classical or quantum, where we have some kind of problem we're trying to solve by developing a machine learning model that maps inputs to outputs, so maybe an image mapping to some classification of that image called the inference step. But what makes it a machine learning problem is that there's a large quantity of training data that's used to set the parameters of this machine learning model in a step that comes before called training, which has its own training algorithm. And it's kind of hard to talk about quantum machine learning because there are many ways in which this can be made quantum. And I think really all of them count as quantum machine learning. So just to give a few examples here, we could leave everything classical but just make the training algorithm quantum. So this is one example of where this was done. There was a proposal to take just big classical neural networks and train them with a quantum algorithm that uses a quantum algorithm for differential equations. We could also make both the training algorithm and the inference algorithm quantum, which is the case in quantum proposals like support vector machines, which I'll talk a little bit about later as well. We could also make the model itself quantum, and we'll see this in quantum neural networks. So in this case, the kind of inference step doesn't even make sense classically because it's written in terms of quantum gates. So really, we need to have a quantum device in order to even understand the model in the first place. And then finally, you could even imagine the data set that you're using to train your model could be quantum. So maybe an example of this is you would have an experiment that collects experimental data about some quantum object like molecules, somehow transduces that into a digital representation that can then be processed, potentially with, it could be classical from their point on, but you could have a quantum algorithm for training on this quantum data. I won't talk too much about that, but that's something to be aware of as well. Okay, so the structure, I guess, here, I maybe at the expense of kind of covering everything a little bit, I decided to focus on two areas in maybe a slightly more depth. The first one is quantum neural networks, or more generally, variational quantum algorithms. And in this area, the key reason that we might hope for there to be a quantum advantage is basically the hope that we know a lot about quantum computing. Like we know that it can do things that classical computers can't do. Right? We know that quantum states live in this very large dimensional vector space that we can't simulate classically. We know that quantum information allows for interference and entanglement and information processing that's fundamentally different than what can be done classically, right? And since big data is sort of about finding patterns, you might hope that this is sort of a new tool that we should try on these big data problems. Just sort of the same way that classical machine learning is kind of not necessarily a known reason why it works. It just kind of is observed to work. We would hope that the same would be true for quantum. So maybe to quickly review the case of classical neural networks in a very basic presentation of that. For classical neural networks, the idea is you have an input which is mapped to an output by this parameterized network of artificial neurons. The input is some image data, and the output is some classification of that image. And there's some loss function which kind of tells you how good the network is doing. And the goal of the training is to take your examples, which in the case of supervised learning would be labeled with some outcome, and try to tune the weights to maximize the performance of the network on the training examples that we have. And this is typically done with some form of gradient descent, so stochastic gradient descent, where the gradients are computed with backpropagation. And backpropagation was, of course, a huge development in neural networks that kind of has enabled it to be scaled to such large sizes. But it's important to emphasize that this is heuristic, right? That there's no necessarily proof of which architectures will work and which won't work, and a perfect understanding of why they work. And analyses in this area are often kind of empirical in nature. So I guess a brief example of a quantum neural network, and this is kind of a very broad category of things, is to replace the artificial neurons in the classical neural network with quantum gates of some kind. This is a very simple example where you would have just 2-qubit unitary gates which process an input, map it to an output, and then make a measurement at the end of the computation to obtain a classical output that can be viewed as the output of the function. So just like classical neural networks, this would map an input to an output, and it has tunable parameters. So of course, a 2-qubit gate has only 4 parameters. It's a 4x4 matrix, so I guess it would have 16 parameters. Often these gates would have just one free parameter, so it would be rotation by some angle. And you would try to optimize your loss function by tuning these parameters to classify the maximum number of examples or something like this. This is also done with gradient descent. But in this case, it's more of kind of a brute force approach typically, where one would kind of have a setting of the parameters, run the circuit on a few examples, perturb the parameters a little bit to estimate the gradient, update the parameters accordingly, and keep going on. Now there's some tricks you can play to improve this gradient estimation, but that's the basic step. And this is also heuristic. Yeah, I should also mention this is there's like a lot of choices here in terms of like how you encode the input, the gates themselves. Like maybe choosing unitary gates is not necessarily the best choice because they're linear. Like we know that the classical neural networks benefit from this nonlinearity in the activation function. So you can put in measurements which are nonlinear, and this can help as well. But this is kind of the high level idea. Okay, so there's a sense in which the quantum neural networks are NISQ friendly, and by NISQ I mean it stands for noisy intermediate scale quantum. This is sort of the opposite of fault tolerant It refers to the era that really we're currently in, where we don't have error-corrected quantum computers. And these neural networks, quantum neural networks, are sort of NISQ-friendly because they are often very shallow. There aren't that many gates involved, and so you can run it, you can get your measurement outcome, and then you can reset, and the noise kind of resets. You don't have to do some really long circuit and keep the coherence the whole time. But nonetheless, maybe a caveat is that eventually, if we do try to scale this up to be extremely large, the size of the classical models that we see today, you would expect the noise to eventually overwhelm these systems. You can do error mitigation. You can really try to squeeze the most you can out of it, but eventually there will be a problem, I guess. There's also a caveat related to the gradients involved in the training process. And there's been a lot of work on this. So one caveat is this phenomenon known as barren plateaus. The idea here is that if you're trying to optimize your loss function, you're trying to find like a local minimum. You're kind of crawling around this high-dimensional optimization space looking for the lowest possible point. And gradient descent is just the rule that you always walk downhill. But what's been observed is that in a large class of quantum neural networks and variational quantum algorithms in general, the landscape is extremely flat. It becomes exponentially close to flat as you increase the system size, causing this gradient descent algorithm to not work very well because you don't know which direction to go if you're kind of on a completely flat landscape. And this is one area that we've already seen sort of a nice mathematical approach to recently in like the last few years. They've kind of, previously they had kind of looked at all these different architectures and seen, oh, there are barren plateaus here, there's barren plateaus here. We can avoid having barren plateaus in this case, but then there's this other outcome. And so this was sort of all unified together into a language of Lie algebras and their subalgebras of the unitary group. So if you're interested in that, you can look into that. And then another caveat, which is maybe related because it's also about the gradients, is that there's no real quantum analog of back propagation that we have for classical neural networks. So if we have a model with m gates or m free parameters, typically we would expect computing the function to kind of scale linearly in cost with m because there's m gates. You just have to do all the gates. That's fine. We kind of expect that. But what's amazing about backpropagation is that the gradients also have a linear cost in the number of parameters. Like computing the gradient is essentially just as hard as computing the function. But for quantum computing, we don't see that behavior. Generally, there's an additional overhead for computing the gradient, and one can get only a kind of square root m overhead here. But yeah, so backpropagation was sort of essential for the fact that classical neural networks have scaled so well. So it would be nice to kind of figure out if this is possible in some sense on the quantum side as well. Oh, and final caveat, I guess when you're thinking about whether quantum neural networks will provide value, I think it's really important to compare to the state of the art on the classical side. And as we all know, classical machine learning is getting really good, and by the time we have large-scale quantum computers, it's going to be even better. So yeah, it's good to keep that in mind when we're projecting for the future. Okay, now I want to change to a completely different area of quantum machine learning, which is using quantum computing in some sense to solve data problems related to linear algebra. This is another area where there have been a lot of proposals in quantum machine learning. And the key idea for why these quantum proposals might give an advantage is really the exponential size of the vector space that the quantum algorithm is using. So in particular, we know that a quantum system with log n qubits is described by a vector in n dimensions. And we can go further and we can look at a quantum circuit with a certain number of gates in it and view that as a sparse matrix vector multiplication in this n-dimensional vector space. So each of the gates is a unitary matrix. It's sparse if it only acts on a few qubits. So if you wanted to simulate this quantum algorithm, you'd have to do this sparse matrix vector multiplication. But of course, the size of n might be far too large to do that on a classical computer. And this kind of resembles a lot of problems in data science, which are also doing high-dimensional linear algebra. So can we utilize quantum computing to help us with these high-dimensional linear algebra problems? A concrete example of this is sort of a very common example in machine learning, which is support vector machines. This is a picture of a support vector machine where we would have it's a supervised learning. So we have two classes of data in our training data. This like purple set and this blue-green set, and we're trying to find the maximum margin hyperplane that separates these two sets. So this is drawn in 2 dimensions, but you should imagine this is a much larger dimensional space than 2. And the goal is to, given a new input, so this yellow one, determine is it part of the purple set or part of the blue set. So if we know what the hyperplane is, then we can just ask which side of the hyperplane are you on. And yeah, this can be difficult because, first of all, there can be a lot of training examples, and also the size of the dimension here could be extremely large. Other example problems that are similar in that they're about linear algebra, for which quantum algorithms have been proposed, include recommendation systems. So this is like the Netflix problem, where you have users who have given they've given ratings for certain things that they've watched, but they haven't watched everything in the library, and now you have to produce a recommendation based on that. The principal component analysis, supervised cluster assignment, Gaussian process regression. These are all similar quantum algorithms and solve kind of similar problems in machine learning. And rather than maybe give the exact details of any one of these quantum algorithms, I thought I would talk about the quantum algorithm for solving linear systems, because many of these algorithms map directly to linear systems, and then the key thing that one does on the quantum computer is solve the linear system. And even the ones that don't map directly to linear systems can, in some sense, still be thought of as something similar. So here we have just a generic linear system, which of course we all know comes up all the time in many areas of applied math. Ax equals b. A is a matrix. X is an unknown vector. B is a known vector. The key parameters here are the condition number of the matrix A. We usually assume that this is not too large. We have well-conditioned matrices, or we regularize them so that they're well-conditioned. And then often in machine learning applications, although not in general, we would have additional assumptions like A might be a low-rank matrix. And the goal, of course, is to find the solution vector X. But on the quantum side, we don't actually end up finding the entire solution vector X. Rather, we prepare a quantum state, ket X, which lives in this n-dimensional vector space and has its amplitudes proportional to the entries of the vector X. So this is different than knowing all the entries of the vector X. It's like this quantum state on log n qubits. And what's remarkable was kind of discovered in the late 2000s, probably one of the most famous quantum algorithms after Shor's and Grover's was the HHL algorithm, which shows that one can prepare this state, ket X, in time that scales linearly with the condition number kappa, but only logarithmically with the size of the vector space. And this can be compared to classical methods for solving linear systems, which always seem to scale at least linearly in the size of the vector space. And of course, this depends on whether it's a sparse matrix. Here I've quoted for dense matrices where like conjugate gradient would have n squared time due to the matrix vector multiplications. Yeah, so in general, if you're writing down the full vector and updating it, you're going to have at least order n times. So you're going to have exponentially longer time in n classically than this quantum algorithm has quantumly. So exponential speed up. Yeah, we did it. But not exactly. I guess there's some caveats to be aware of, and this doesn't mean that this can't be utilized effectively, but one has to be very careful. And the first reason is the output problem, which is that we didn't actually solve the same problem on the quantum computer that these iterative classical algorithms solve. We prepared this quantum state ket X, which encodes the amplitudes into its encodes the solution into its amplitudes. But when we measure the state, we just get a random outcome that's biased toward the coefficients that have a larger magnitude. So if we wanted to actually learn the entire state, we would need order n copies of this state to like learn those amplitudes, and then our exponential speedup would be gone. Additionally, if we want to even learn one quantity, for example, one of these entries or some inner product with this vector, we can do that. It doesn't scale with n, but it does scale with the precision, like 1 over the precision, which is sort of not the best. Like we would prefer a log 1 over epsilon scaling there, but that's known to be impossible. So this means that when we're designing our end-to-end quantum algorithm, we really need to make sure that we really only need to know 1 or 2 quantities from this output state. We don't need to actually learn the whole state. We can sort of extract what we need very efficiently. And this is the case in many of these examples. So support vector machines, for example, you prepare a state, and then you can classify a new vector just by computing an inner product with this solution vector. You don't actually have to learn all of the entries. So sometimes this output problem can be solved, but it is something to be aware of. Another caveat is the input problem. And you might have observed that I just said that we had a polylogarithmic time algorithm for a problem that involves a data set of size order n, which already requires order n time to even write down in the first place. So how is this possible? Is there a catch? And I guess the answer is that it was possible using essentially parallelism via the assumption of a quantum RAM. So what is quantum RAM? Quantum RAM is like classical RAM. You have a classical database. You have an index. You want to like find the element of the database that corresponds to the index. The only difference is that now the index can be in a superposition. And we would like to query our database. We would like to pull in the value from the database in a way that doesn't destroy the superposition that we began with. And the assumption in many of these quantum machine learning algorithms is that this quantum RAM operation can be performed in only logarithmic time. But this is a bit controversial, and there's a few reasons for this, and there's actually a really good review by Jacques and Ratu that kind of goes through all of this in great detail. Basically, this assumption of log depth RAM is mostly true in the classical case, but in the quantum case, it gets complicated by the fact that quantum gates are kind of really active interventions. They're not just kind of circuits etched on a chip. They're also not exactly compatible with noise. The noise really complicates this a lot. And there's also really no compelling proposal yet for a large-scale hardware implementation of this QRAM. So it's sort of controversial. And if we don't have this assumption of cheap, large-scale quantum RAM, then this exponential speedup can't be possible. Okay, the third caveat is dequantization, which is that even if we've solved the output problem, we've solved the input problem, we really need to make sure we compare against the best, or the analogous classical algorithm that uses the same assumptions. And sort of surprisingly, after there had been a period of time where we thought that there were these exponential speedups in quantum machine learning, in around 2018, it was discovered that there are classical algorithms acting under a very similar kind of access model called the sample and query access model, which also have a runtime that's independent of the vector space dimension n. Or actually, it's logarithmic in the vector space dimension n. So this is polynomially worse than the quantum algorithm, leaving open the possibility of a polynomial speedup, but kind of removing hope of an exponential speedup in most cases. So a lot of these algorithms have been dequantized, although not quite all of them. There are a few edge cases where there could yet be an exponential speedup. Okay, I have about a minute left on the timer. I have a few more slides, so I just want to go through it really fast. There's a few topics I didn't cover, which I just wanted to mention and show that they exist in case any of them pique your interest. So topological data analysis, learning theory, energy-based generative models, tensor PCA. I don't know why I did that. This example I mentioned of training the sparse neural networks with quantum algorithms for differential equations. Yeah, I still had 30 seconds left. I don't know, is this... Oh, okay. Um, yeah. Yeah. There's a lot more topics that exist. Yeah. I guess technical opportunities. I really want to emphasize that there's a lot of reasons to be maybe pessimistic about some of this machine learning stuff that I tried to lay out here. Some points of caution, but the bull case for quantum machine learning is that, like, if we look at what happened with classical machine learning, these heuristic algorithms just worked a lot better than we expected. And we only discovered that once the hardware became available. So I think there's really an opportunity to figure out how do we gather evidence for or against these heuristic algorithms in the meantime, before we have the hardware to actually run them. So that's, maybe one place applied math can help. Then I guess, yeah, connecting these machine learning capabilities with actual end-to-end problems that people care about in other areas. I had this table comparing to other application areas, so maybe I can talk in person with people if you're curious about kind of the relationship here. This was just to say that one thing that distinguishes machine learning is that the data input is really big, and a lot of these other application areas are the opposite. The data input is very small. So like Shor's algorithm, it's like a 2,000-bit number. It's like, a few hundred bytes of input data, which is the complete opposite of these big data problems. And since Shor's algorithm is maybe the best quantum algorithm, this is maybe one reason to be a bit skeptical of big data problems for quantum computing. Yeah. Okay. That's it. Thank you.